The morning of July 23rd, 1944, a Wehrmacht repair depot 15 kilometers behind the Normandy front lines. The air was thick with the smell of burned rubber and diesel fuel, and Obergefreiter Klaus Richter stood before something that would shatter everything he understood about engineering. It was an American M4 Sherman tank, captured intact after its crew abandoned it when the right track was blown off by a Panzerfaust. The hull was scarred but functional. The engine, when they'd tried it, turned over on the first crank. And according to the odometer, a detail that had caused considerable discussion among the mechanics, this particular Sherman had travelled 3,214 kilometers since leaving the factory. Nearly 2,000 miles. Klaus was a transmission specialist. Before the war, he had worked at the Zahnradfabrik Friedrichshafen, building gearboxes for German trucks and military vehicles. He understood tolerances measured in hundredths of a millimeter. He understood heat treatment schedules and bearing preload specifications. He understood that precision engineering was what separated German machinery from the crude implementations of other nations. But standing there, looking at the Sherman's open hull, his hands still greasy from the inspection, Klaus understood nothing at all. This should not be possible, he said to Feldwebel Hartmann, his immediate superior. The wear patterns alone should have caused catastrophic failure at least 1,000 kilometers ago. Hartmann, a career soldier who had fought in Poland and France before being relegated to depot duty after losing 2 fingers to frostbite in Russia, looked at him with eyes that held a particular kind of exhaustion. And yet, he said quietly, we keep finding them, hundreds of kilometers from any American supply line, still running, still fighting. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The order to disassemble and document the Sherman's drivetrain had come from Berlin itself. The High Command was desperate to understand why American armor, theoretically inferior in every measurable way, kept appearing in places it had no business being, why German tanks, marvels of engineering precision, seemed to spend more time in repair depots than on the battlefield, while these crude American boxes kept rolling forward. What Klaus discovered over the next 4 days would not just challenge his understanding of mechanical engineering, it would reveal 2 entirely different philosophies of war, and only one of them was designed to win. To understand what shocked Klaus Richter and his team, you must first understand what they expected to find. You must understand the German philosophy of engineering that had shaped not just their tanks, but their entire approach to modern warfare. German tank design in the Second World War was built on a foundation of principles that stretched back to the 19th century, to the workshops of Krupp and the drawing boards of the Imperial German Navy. It was a philosophy expressed in a single word: precision, precision, not merely as a manufacturing goal, but as an almost moral principle. The Panzer V Panther tank, which by mid-1944 had become the backbone of German armoured forces in the West, embodied this philosophy completely. Its Maybach HL 230P30 engine produced 700 horsepower through a complex fuel injection system. Its AK-7-200 transmission featured 7 forward gears and 1 reverse, each gear individually machined from solid steel billets, heat-treated to exact specifications, then ground to tolerances that required specialized measurement equipment to verify. The transmission alone weighed over 700 kilograms. It took 4 men and a specialized hoist to remove it from the vehicle. The official maintenance manual for the Panther's drivetrain ran to 412 pages and required 3 separate volumes to contain all the specialized procedures and torque specifications. But this was not seen as a flaw. This was the point. German engineering doctrine held that war was won through technological superiority, through building machines so advanced, so precisely manufactured, that they would overwhelm the enemy through sheer quality. Each Panther represented hundreds of hours of skilled labor, incorporating metallurgical advances and design features that were genuinely at the cutting edge of 1944 technology. Klaus himself had been trained in this tradition. At Zahnradfabrik Friedrichshafen, he had learned to measure clearances with micrometers, to calculate gear ratios to 3 decimal places, to understand the complex relationship between contact patterns and load distribution. He had been taught that German engineering was the finest in the world, because Germans were unwilling to accept the compromises that lesser nations made, and it was precisely this uncompromising approach that was destroying them. By July of 1944, Klaus's depot was receiving a steady stream of Panthers with catastrophic transmission failures. The official designation was Antriebsschaden drivetrain damage, but the mechanics had their own term for it, Getriebehölle, transmission hell. The symptoms were consistent and devastating. After approximately 150 kilometers of operation, sometimes less in combat conditions, the Panther's final drives would begin to fail. The first sign was usually a high-pitched whine from the transmission, indicating that gear teeth were beginning to pit under the extreme loads. Then would come the grinding sensation as damaged teeth began catching. Finally, catastrophic failure. Shattered gear teeth, seized bearings, sometimes the entire transmission casing cracking under the stress. Klaus kept records. Between June 6th, when the Allied invasion began, and the day the Sherman arrived at his depot, he had personally overseen the attempted repair of 37 Panthers with major drivetrain failures. Of these, only 9 had been successfully returned to service. The rest required complete transmission replacements, components that were not available, that could not be manufactured quickly enough, that were sitting in factories back in Germany, that were themselves under increasingly heavy Allied bombing. The Panther that had arrived 3 days before the Sherman was typical. It had travelled exactly 162 kilometers from the railhead where it had been unloaded. The crew reported that the transmission had been tight from the beginning, requiring more force than normal to shift gears. By the time they reached their assigned position, the grinding was audible even over the engine noise. During their first engagement with Allied forces, the transmission had seized completely in 3rd gear. Unable to shift, unable to reverse, the crew had been forced to abandon the tank when American infantry began working around their flanks. When Klaus's team opened that transmission, they found a textbook example of precision engineering destroying itself. The gear teeth showed perfect contact patterns, evidence of expert manufacturing, but those same gear teeth had been loaded beyond their design limits. The steel, heat-treated to extreme hardness for wear resistance, had become brittle. Under the stress of combat driving rapid acceleration, sudden direction changes, the enormous torque loads of moving a 45-ton vehicle across rough terrain, the brittle teeth had simply shattered. It was the paradox at the heart of German tank design. They had optimized for perfection in ideal conditions, but war provided no ideal conditions. The Panther's transmission required constant maintenance. Daily, the crew had to check oil levels in the transmission, the final drives, and the steering gearboxes. Every 50 kilometers of operation, the track tension had to be adjusted too loose, and the tracks would throw under hard turns, too tight, and the additional stress would accelerate final drive wear. Every 100 kilometers required a complete inspection of the entire drivetrain, checking for oil leaks, measuring bearing temperatures, examining the teeth of the drive sprockets for wear, adjusting the clutch engagement points. This maintenance could only be performed properly with the correct tools and considerable technical expertise. A Panther crew typically included at least one member with specialized mechanical training. Even then, many procedures required depot-level facilities, lifts to raise the tank, specialized tools to access certain components, precision measuring equipment to verify that adjustments were within specification. And even with all of this expert care, even with mechanics like Klaus doing everything exactly according to the manual, the Panthers kept failing. The German approach was based on an assumption that they would fight a war where rear areas were secure, where supply lines were intact, where damaged vehicles could be withdrawn to proper repair facilities and maintained by factory-trained technicians using correctly manufactured replacement parts. But by July of 1944, that war no longer existed. The rear areas were under constant air attack. The supply lines were interrupted by Allied fighter bombers that owned the skies. The factories were being bombed around the clock, and the Panthers, these marvels of precision engineering, were dying not from enemy fire but from their own complexity. Klaus knew all of this. Every mechanic at the depot knew it. They could see the reality in every seized transmission, every cracked final drive, every perfectly machined gear tooth that had shattered under loads it was never meant to bear. And then they opened up the Sherman. The Sherman that sat in Klaus's workshop bay was a late-production M4A3 manufactured by the Pressed Steel Car Company in Pennsylvania sometime in early 1944. It had the Ford GAA V8 engine and the standard Spicer manual transmission. According to the data plate, it had been assigned to a unit of the 2nd Armored Division. The exterior told a story of hard use. The hull was covered in scratches and dents, the paint worn off in patches from the constant rubbing of equipment and crew movement. There were weld repairs visible on the lower hull, evidence of previous battle damage that had been fixed in the field. The tracks were worn but functional, each pad showing the characteristic pattern of contact with road surfaces and the gradual wear from the drive sprockets. But it was running. After 3,000 kilometers, after being driven from the beaches of Normandy through the hedgerow country, after countless engagements and uncounted hours of operation, it was still running. Complete drivetrain analysis, Hartmann ordered. Engine, transmission, final drives. We need to document everything. Measurements, photographs, technical drawings. Berlin wants to know how they're achieving these operational ranges. Klaus began with the external inspection. The Sherman's hull was noticeably smaller than a Panther's, despite the two tanks having similar combat weights. Where the Panther's silhouette was dominated by the massive turret and the sloped frontal armor, the Sherman was more compact, almost utilitarian in appearance. The track width was narrower 16.5 inches compared to the Panther's 26 inches, which meant higher ground pressure, but also meant the Sherman could fit down roads and through gaps that a Panther couldn't. Navigate. The engine access was shockingly simple. Where a Panther required the rear deck to be unbolted and a hoist to lift the entire engine and transmission assembly, the Sherman had a simple armored panel that could be opened with basic tools. Looking into the engine compartment, Klaus could see the entire powertrain, the Ford GAA engine, the transmission bolted directly behind it, the drive shaft running forward to the differential in the nose. We'll need to pull the transmission, Klaus told his team. Full disassembly and inspection. What happened next would become, in the years after the war, when Klaus told this story to his engineering students, the moment when he began to understand that he had been asking the wrong questions about tank design. It took 4 men 3 hours and 40 minutes to remove the Sherman's transmission. No specialized tools, no factory-trained technicians, no hoists or overhead cranes, just basic hand tools, the procedures helpfully stenciled in English on the hull interior, and torque specifications that were marked directly on the transmission casing itself. 3 hours and 40 minutes. Klaus had been part of crews that took 3 days to remove a Panther transmission. They laid the Sherman transmission on the workshop floor and began the disassembly. This took another 2 hours. Again, no specialized tools were required. The casing was held together with standard bolts. The gears were retained with snap rings that could be removed with basic pliers. The entire assembly was designed to come apart in a logical sequence that even a relatively inexperienced mechanic could follow. And then they saw the gears themselves, and Klaus felt something cold settle in his stomach. The Sherman's gears were crude. There was no other word for it. Where German transmissions used precisely machined helical gears with complex tooth profiles designed to distribute loads evenly and reduce noise, the Sherman used simple spur gears with straight-cut teeth. The machining marks were visible on the gear faces in a German transmission. These would have been ground away as a sign of poor manufacturing. The gear teeth showed significant wear. The edges were rounded, the surfaces scored with fine scratches. Under magnification, Klaus could see pitting in the metal evidence of the constant hammering action of gear teeth coming into and out of contact under load. "This transmission is worn out," one of the younger mechanics said. "It should have been replaced at least 1,000 kilometers ago." But Klaus was staring at something else. He had pulled the oil filter and cut it open to examine the contents. The filter material was saturated with metal particles, tiny fragments of steel worn away from the gears, the bearings, the shafts. In a German transmission, this level of metal contamination would be a death sentence, an absolute indicator of imminent catastrophic failure. He looked at the odometer reading again. 3,214 kilometers. "Get me the bearing clearances," he told his team. "Measure everything. I want to know exactly how worn these components are." The measurements told an impossible story. The bearing clearances in the Sherman transmission were enormous by German standards in some cases, 10 times what would be considered acceptable in a Panther. The shaft-to-housing clearances were similarly oversized. Even the gear mesh spacing, the critical distance between mating gear teeth, was loose enough that Klaus could see visible gaps when the gears were assembled. "This is not precision manufacturing," he said slowly. I don't know what this is." Hartmann, who had been watching the disassembly with increasing interest, knelt down beside the transmission. He reached out and spun one of the gears with his remaining fingers. It rotated easily on its shaft, wobbling slightly from the loose bearing fit. "It's designed to be sloppy," Hartmann said quietly. "That's intentional," Klaus wanted to argue. Everything in his training told him this was wrong. Tight tolerances were good. Precision was good. These wide clearances, these crude gears, this entire design philosophy was the opposite of everything he had been taught about proper engineering. But he couldn't argue with the odometer. 3,214 kilometers. He spent the next 2 days studying that transmission. He measured wear patterns on every gear tooth. He documented the bearing clearances at multiple points on each shaft. He cut open every oil seal and examined it under magnification. He took apart the synchronizers and studied how they were designed. He even removed and disassembled the shifter mechanism itself to understand how the Americans had made gear selection so simple. And slowly, reluctantly, Klaus Richter began to understand what he was looking at. The Sherman transmission wasn't designed to prevent wear, it was designed to tolerate it. Those wide bearing clearances meant that as bearings wore, the shafts had room to move slightly without causing catastrophic failure. The loose gear mesh meant that as teeth wore down, the gears continued to engage properly instead of binding. Even the simple spur gear design, which Klaus had initially dismissed as primitive, had advantages. Spur gears generated axial thrust loads, but they were also more tolerant of misalignment and easier to manufacture to consistent standards. The Americans had built a transmission that assumed wear would occur. They accepted it. They designed it around it. Instead of trying to prevent every possible degradation through precision manufacturing, they had created a system that continued functioning as it degraded. It was, Klaus slowly realized, a completely different philosophy of engineering. The Germans built transmissions that worked perfectly when new and failed catastrophically when worn. The Americans built transmissions that worked adequately when new and continued working adequately even when worn. And in a war, adequate beat perfect every single time. The report Klaus wrote, working late into the nights by a lamplight, while Allied bombers droned overhead on their way to targets deeper in Germany, ran to 23 pages. Fragments of this report survived the war and were captured by American intelligence officers who found them in Wehrmacht archives. Klaus didn't know it at the time, but he was documenting his own obsolescence. He began with the technical specifications because this was how he had been trained to think. The Sherman Spicer transmission weighed approximately 320 kilograms, less than half the weight of a Panther transmission. It featured 5 forward speeds and 1 reverse. The gear ratios were widely spaced compared to German practice, which meant less flexibility in matching engine speed to vehicle speed, but also meant simpler operation and more durable gears. The transmission casing was cast rather than machined from solid billets. This was cheaper and faster to produce, but it also meant the casing had flexibility that absorbed shock loads instead of transferring them directly to the gears. Klaus noted this with the German technical term for such a design choice, elastische Struktur, elastic structure. He didn't use the term approvingly. German engineering preferred rigid structures with precisely controlled deflections, but he had to note that the American approach seemed effective. The Americans had done something else that Klaus found almost offensive in its crudity. They had designed the entire drivetrain as modular, interchangeable components. The engine, transmission, and final drives were all separate units that could be swapped out independently. More than that, they had standardized these components across multiple vehicle types. The same transmission used in the Sherman was used in modified form in American tank destroyers and heavy trucks. This meant that American supply lines only needed to stock a few different component types to maintain an entire range of vehicles. It meant that field mechanics didn't need specialized training for each vehicle. Once you knew how to remove and replace a Sherman transmission, you knew how to do it on half a dozen other vehicle types. It meant that repair depots could focus on rebuilding components rather than performing complex in situ repairs. It was, Klaus had to admit, brilliantly practical. And it was completely contrary to German practice. German vehicles were highly specialized. A Panther transmission could only be used in a Panther. The tools required to maintain a Panther were different from those required for a Tiger. Even different production batches of the same vehicle sometimes required different maintenance procedures as running design changes were incorporated. This specialization allowed for optimization. Each vehicle could be tuned for its specific role, but it created a logistical nightmare. Klaus documented the maintenance implications. The Sherman's engine oil and transmission oil were the same type standard SAE 30 weight. German tanks required different grades of oil for different components, and switching or mixing them could cause failures. The Sherman's transmission could be drained and refilled without removing it from the vehicle, a simple operation that took less than an hour. Changing transmission oil in a Panther required partial disassembly of the drivetrain and a full day's work. The Americans had even, and Klaus found this detail almost incomprehensible, designed the Sherman transmission to be rebuilt in the field. The service manual included instructions for replacing worn gears without specialized equipment. The tolerances were loose enough that new gears could be fitted without precision shimming or bearing preload adjustments. An American ordnance company could set up a transmission rebuild facility anywhere with basic machine tools and turn out functional units within hours. The implications of this were staggering. It meant that the American supply chain didn't need to reach all the coast way back to factories in Detroit. Field depots could remanufacture components, keeping the armor moving forward while damaged parts were cycled back for proper rebuilding. German practice was the opposite. Damaged transmissions were returned to Germany when this was possible at all for factory rebuilding. This took months. In the meantime, tanks sat idle, waiting for replacement components that were caught somewhere in a supply chain that was under constant Allied air attack. But Klaus's report went beyond mere technical specifications. He tried, in careful German military prose, to explain what he was beginning to understand about American industrial philosophy. The enemy transmission, he wrote, is not designed for longevity in individual components, but for sustained operational capability of the overall force. Where German engineering seeks to maximize the performance of each unit, American engineering seeks to maximize the availability of functional units. This approach accepts higher individual component failure rates as the cost of maintaining overall force readiness. He documented the evidence he had found of the Sherman's operational history. The tank had clearly received field maintenance multiple times. There were weld repairs on the hull where damaged areas had been cut out and patched. The engine, when they removed it for inspection, showed signs of being a replacement unit. The production date on the engine block was 3 months later than the date on the hull's data plate. This was normal American practice, Klaus learned from interrogating the captured crew. When an engine failed, you didn't repair it in place. You pulled out the entire power pack engine, transmission, and associated systems as a unit and installed a replacement. The damaged unit went back to a depot for rebuilding. The entire swap could be done in a few hours with a crane and a trained crew. The Americans, Klaus wrote, treat their tanks as they treat their trucks, as expendable tools to be used, maintained at a minimal level, and replaced when no longer functional. There is no sense of mechanical sympathy, no attempt to optimize performance, no recognition of the artistry involved in precision manufacturing. It is pure industrial pragmatism. He meant it as criticism, but reading his own words, Klaus couldn't shake the growing realization that this industrial pragmatism was winning the war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical analysis was disturbing enough, but what truly shook Klaus was what he discovered about American production capabilities when he began comparing the numbers. The Panther transmission that sat in pieces in the adjacent workshop bay had been manufactured by Zahnradfabrik Friedrichshafen, Klaus's own former employer, in April of 1944. It was one of approximately 250 Panther transmissions produced that month. This was considered good production. Zahnradfabrik Friedrichshafen was one of Germany's premier transmission manufacturers, employing thousands of skilled workers and operating some of the most advanced machine tools in Europe. The Sherman's transmission had been built by the Spicer Manufacturing Company in Toledo, Ohio. Klaus had never heard of them before. Using the serial number and cross-referencing with captured American documents, he was able to determine that this transmission had been one of approximately 3,800 units produced in the same month. 3,800 transmissions. In 1 month, from one factory. Klaus checked his calculations 3 times because he couldn't believe the numbers. Spicer Manufacturing was producing more Sherman transmissions in a single month than Germany was producing complete Panther tanks in 3 months. He expanded his research, studying every captured American document he could find, interrogating every prisoner who might have information about industrial production. The picture that emerged was almost incomprehensible to someone raised in the German system. The United States had 6 major manufacturers producing Sherman tanks and components. These manufacturers were supported by hundreds of subcontractors who produced everything from rubber track pads to periscope lenses. The entire system was designed for volume production using semi-skilled labor. Where German tank factories relied on craftsmen who had spent years learning their trades, American factories hired workers off the street and trained them to perform specific, repetitive tasks. This approach meant that American production could scale rapidly. When the war began, most of these factories had been producing civilian goods, automobiles, tractors, refrigerators. They had converted to war production not by completely retooling, but by adapting their existing mass production techniques to military hardware. The same assembly line processes that had made Ford's Model T affordable to millions of Americans were now churning out Sherman tanks at a rate that Klaus found almost impossible to believe. By July of 1944, American factories had produced approximately 45,000 Sherman tanks in all variants. They were producing roughly 2,000 new vehicles per month, and this production rate was increasing, not decreasing, despite the fact that the factories themselves were under no threat of air attack. Germany, fighting for its survival, had produced approximately 6,000 Panther tanks since the type entered service in 1943. Current production was approximately 300 units per month, and this was declining as Allied bombing intensified and critical material shortages worsened. Klaus stared at these numbers for a long time. The implications were brutal. Even if the Panther was superior to the Sherman in direct combat, and by 1944 this wasn't even clear anymore, it didn't matter. The Americans could afford to lose 7 Shermans for every Panther and still come out ahead. They could afford to have transmission failures and simply replace the entire unit. They could afford to have tanks destroyed and built faster than they were being lost. Germany couldn't afford any of this. Every Panther represented hundreds of hours of skilled labor that couldn't be replaced. Every transmission failure meant a tank that would sit idle for weeks, waiting for parts that might never arrive. Every combat loss was a loss the German industry had no hope of making good, but it went deeper than just production numbers. Klaus was beginning to understand that the Americans had made a fundamental choice about how to fight an industrial war, and it was a choice that Germany had never even considered. The German approach was to build the best possible weapon and then build as many as possible with available resources. Quality first, then quantity. The assumption was that superior weapons in the hands of superior soldiers would defeat numerically larger forces of inferior quality. The American approach was to build adequate weapons that could be produced in overwhelming numbers. They had consciously chosen to sacrifice individual unit performance for overall force capability. A Sherman wasn't as good as a Panther in a one-on-one engagement, but there would never be a one-on-one engagement. There would be 5 Shermans for every Panther, and those Shermans would be supported by artillery, close air support, and an industrial base that could replace losses faster than they occurred. It was a choice that only a nation with America's industrial capacity could make. But it was also a choice that Germany, with its emphasis on craftsmanship and engineering excellence, would never have made, even if it had the capacity. Klaus tried to express this in his report, but he struggled to find the right words. How do you explain to German officers, raised on Prussian military traditions and pride in German industrial achievement, that the enemy was winning by being deliberately crude, that American factory workers, with minimal training, were producing weapons that were defeating the products of Germany's finest engineers? The fundamental difference, he finally wrote, is that the Americans have designed their equipment to be operated and maintained by average soldiers with minimal training, while we have designed our equipment to be operated and maintained by specialists. In a short war, our approach would be superior. In a long war of industrial attrition, theirs is unbeatable. He didn't write what he was actually thinking, that by July of 1944, the war was already lost. Every time a Panther broke down, waiting for parts that weren't coming while Shermans rolled past, the war was lost again. That German engineering excellence had become a liability, not an asset. The transmission sat reassembled on the workshop floor, all its crude, worn, inadequate parts fitting back together with their sloppy clearances and visible machining marks. Klaus had documented everything: gear, tooth wear patterns, bearing journal measurements, oil contamination levels, the flexibility of the cast casing, the simplicity of the assembly process. It was a transmission that by every German standard should have failed 1,000 kilometers ago, and yet it had run for 3,000 kilometers, and given proper oil and basic maintenance, it would probably run for another 1,000 before finally wearing out completely. And when it did wear out, the Americans would simply unbolt it, drop in a replacement, and be back in action within hours. The worn-out unit would go back to a depot where semi-skilled workers would replace the damaged gears, install new bearings, and send the rebuilt transmission back to the front. The entire cycle was designed to keep tanks moving forward, always forward, with a relentlessness that had nothing to do with the quality of individual components and everything to do with the overwhelming scale of American industrial might. Hartmann came to look at the finished analysis. He read Klaus's report slowly, his damaged hand tracing the lines of text. When he finished, he was quiet for a long time. "You know what's going to happen with this report," Hartmann finally said. "Someone in Berlin will read it and they'll say, yes, we understand the Americans have quantity, but we have quality. That's what will win the war." Klaus nodded slowly. He knew. "They won't understand," Hartmann continued. "That quality is only valuable if you can sustain it. That building perfect tanks doesn't matter if they spend more time broken than fighting. That having the best trained crews in the world doesn't matter if you can't fuel or maintain your vehicles." He looked at the Sherman transmission sitting there on the Reddit workshop floor. "We're losing to crude engineering and mass production," Hartmann said. "Not because their individual tanks are better, but because they can field 5 to every one of ours, and they keep running while ours break down. We're losing because we built weapons for the war we wanted to fight, and they built weapons for the war that actually exists." Klaus started to respond, but an air raid siren cut him off. They could hear the heavy drone of 4-engined bombers in the distance, heading east toward targets deeper in Germany. probably industrial targets, probably factories like Zahnradfabrik Friedrichshafen, where skilled craftsmen were desperately trying to produce enough transmissions to keep the Panther force operational. They stood there in the workshop, listening to the bombers pass overhead, and Klaus understood with perfect clarity that they were standing inside a paradox. German engineering excellence had created weapons so sophisticated that only Germany could build them. And now that German industry was being systematically destroyed by Allied air power, those weapons were becoming irreplaceable heirlooms rather than tools of war. The Sherman transmission, crude as it was, represented something that Germany couldn't match: resilience through simplicity. The Americans had designed for a war of attrition, accepting that nothing built by human hands was perfect, and that in a long war, good enough, in vast quantities, would always defeat perfect in limited numbers. 3 days later, Klaus's depot received orders to evacuate. Allied forces had broken through the German lines 30 kilometers to the west. They had 4 hours to destroy sensitive equipment and withdraw. Klaus never found out what happened to his report. He suspected it ended up in a filing cabinet somewhere, read by staff officers who nodded thoughtfully, and then went back to demanding better performance from tanks that were engineered to tolerances the supply chain could no longer support. The Sherman, missing its track and incapable of being repaired with the limited time and equipment available, was destroyed in place. Klaus set the demolition charges himself, placing them carefully around the transmission that had occupied his thoughts for 4 days. Before lighting the fuse, he took one last look at those crude gears with their excessive clearances and visible wear. He thought about the American crew that had driven this tank 3,000 kilometers from the beaches of Normandy. Average soldiers, probably, with minimal mechanical training. They had performed basic maintenance, changed the oil when required, and otherwise simply driven the vehicle without the constant attention and specialized knowledge that a Panther demanded. When something broke, they had probably replaced it with a spare part from the supply and kept going. And it worked. God help him. It had worked better than precision engineering and decades of German industrial expertise. The charge detonated as Klaus and his crew drove away, a sharp crack followed by secondary explosions as the fuel and ammunition cooked off. Another dead Sherman, one of thousands that would be lost in the drive across Europe. And unlike the Panthers being abandoned all across France for lack of spare parts or trained mechanics, this Sherman would probably be replaced within a week by another crude, adequate vehicle rolling off an assembly line in Pennsylvania. Klaus Richter survived the war. The depot withdrew successfully, though they lost 2 trucks to Allied fighter bombers during the retreat. He was captured by American forces in April of 1945, spent 18 months in a prisoner of war camp, and returned to Germany to find Friedrichshafen heavily damaged by bombing. He got a job with the American occupation authorities, advising on the reconstruction of German industrial capacity. Later, when Mercedes-Benz resumed civilian production, he was hired as a senior engineer working on truck transmissions. In 1953, Mercedes engineers were developing a new transmission for heavy trucks. They had designed a complex unit with precisely machined gears and tight tolerances, traditional German engineering. Klaus, now the head of the transmission development department, reviewed the design and made a suggestion that shocked his colleagues. "Make the clearances looser," he said. "Use simpler gear profiles. Design it so that a truck driver can do basic maintenance without specialized training." The younger engineers were horrified. This was crude. This was compromising quality. This wasn't the Mercedes way. Klaus pulled out a folder from his desk. In it were copies he had made of his 1944 report on the Sherman transmission, along with photographs of the components and his detailed measurements. He had kept these for 9 years, studying them periodically, understanding more each time about what they really represented. "This is a transmission," he told his team, "that ran for 2,000 miles without major maintenance, that could be repaired by average mechanics in a few hours, that was so simple that millions of them were built to consistent quality standards, and it helped win a war." He let them examine the photographs, the measurements, the documentation of those crude spur gears with their excessive wear. "We lost," Klaus said quietly, "partly because we believed that perfection was always better than adequacy, that precision was always superior to simplicity, that the best way to win was to build the very best machines and then build as many as we could afford." He pointed at the Sherman transmission specifications. "They won because they understood something we didn't, that in the real world, especially in war, availability is more important than capability. That building adequate equipment you can produce in quantity and maintain easily is better than building perfect equipment that's too complex for the actual conditions it will face. That good enough, delivered on time and in volume, beats perfection that arrives late and in limited numbers." The transmission they eventually designed incorporated Klaus's suggestions. It was simpler than traditional Mercedes transmissions, more tolerant of wear, easier to maintain. It wasn't as sophisticated as what German engineers were capable of building, but it worked, and it kept working, and it could be serviced by mechanics at truck stops across Europe without specialized factory training. Klaus never called it the Sherman philosophy, but that's what it was. A lesson learned in a workshop in Normandy in July of 1944, looking at crude American gears that had run for 2,000 miles and would have run for 2,000 more. There's a footnote to this story that's worth knowing. After the war, American military engineers examined captured German tanks and equipment. Their reports, many of which were only declassified in the 1980s, make for fascinating reading. The engineers were genuinely impressed by German manufacturing quality. They noted the precision of the machining, the sophistication of the designs, and the clear evidence of highly skilled labor. One report on the Panther specifically praised the transmission as arguably the most advanced design of its type in the world. The key word there is advanced, not best, not most, effective, advanced. Because by 1945, American engineers had figured out what Klaus Richter learned in his workshop, that advanced and effective were not always the same thing, that you could build the most sophisticated transmission in the world and still lose the war if you couldn't produce enough of them, couldn't maintain them in field conditions, couldn't keep them running under the actual stresses of combat operations. The Sherman tank went on to serve in militaries around the world for decades after World War II. Modified versions fought in Korea, in the Middle East, in conflicts across South America and Asia. Many were still in service in the 1970s, 30 years after they rolled off American assembly lines. Some of them, incredibly, were still running on their original transmissions. Crude, worn, adequate transmissions with clearances that would have horrified Klaus Richter in 1938, but that by 1944 had taught him the difference between engineering and war. The last Panther in operational condition is in a museum. It runs periodically for demonstrations, maintained by expert restoration specialists, using carefully manufactured reproduction parts. Because the original supply chain that built it no longer exists and never could be recreated, it is a monument to German engineering excellence, a beautiful, sophisticated, deadly machine that was obsolete before it even reached the battlefield, not because it wasn't good enough, but because it was too Good for the war it was built to fight. Klaus Richter died in 1978. According to his children, he kept a photograph on his desk until the end. A grainy black and white image of a Sherman transmission laid out on a workshop floor, its crude gears and excessive clearances visible even in the poor quality of the wartime photo. Below the photograph, he had written a single line in English, a language he had learned during his time working with the American occupation authorities. Good enough wins. It was a lesson that cost Germany a war to learn, a lesson about the difference between what engineers want to build and what soldiers need to use, about the gap between theoretical excellence and practical effectiveness, about how sometimes the most sophisticated solution is exactly what defeats you. The Sherman transmission that Klaus Richter inspected in July of 1944 was not a marvel of engineering. It was something more important than that. It was adequate, producible, maintainable, and above all, sufficient for the task at hand. And in the brutal arithmetic of industrial warfare, sufficient beats perfect every single time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.